Hello everyone, and welcome back to my SP2 channel. This lesson is all about the limiting reagent, a little bit on the theoretical and the percent yields, and just like always, we have a practice for you at the end. Okay, so the concept of limiting reagent can be a challenging topic in chemistry, and many of us have a struggle with it. In this session, I aim to simplify it for you and make it a little bit more engaging by using a relatable analogy, which is the analogy of making burger sandwiches. Okay, so let's say your plan is to make several sandwiches using two buns, one burger patty, one slice of cheese, and I'm going to summarize them as the following. So I have my B as bun, I have my burger patty, which is P. C is going to be the slice of cheese. And then your sandwich would be B2PC. Okay. You can balance your recipe here as 2B plus P plus C that goes to B2PC. Okay. Yum, yum. Now, let's say that I have these ingredients. I have 8 buns, I have 6 burger patties, and I have 10 slices of cheese. Okay, so now I want to think about how many sandwiches we actually can make with these ingredients. Okay, so think about it for a moment and then follow me on the next page. Okay, so to answer this question, we need to calculate our sandwiches based on each ingredient. Okay, so starting by buns. Each sandwich requires 2 buns. So if I have 8 buns, I can make 4 sandwiches. For the burger patties, I know that each sandwich requires 1 patty. So if I have 6 patties, I should be able to make 6 sandwiches, right? For the cheese or the slices of the cheese, each sandwich requires 1 slice. So I have 10 slices. That means I can make 10 sandwiches. Okay, now, which one is really the answer? Well, the answer is going to be only 4 sandwiches, right? Because once you're done with all the buns, we're not going to make any more sandwiches, right? So after making 4 sandwiches, we're going to have the leftovers as the 2 burger patties and 6 slices of cheese. Okay, so this example is actually helping us, understanding the limiting reagents, right? Which is always limiting how much product, in this case, our sandwiches, can be made, right? So a similar situation often happens in chemical reactions when one reactant is used up before the others. Now, the reaction is going to be stopped as soon as any of the reactant is completely consumed, right? And that is going to give us the rest of the reactants as the leftovers. The reactant that is completely consumed in our reaction is always known as your limiting reactant, right? Because that is the one that is determining or limiting how much product can be formed. And the other reactants are often referred to the excess reactant. Now, let's take a look at examples. So here it says we have a mixture of 10 moles of hydrogen and 7 moles of oxygen gases. We're going to let them react so they can make water molecules. This is your reaction, and again, it has to be balanced, right? So the reaction is already balanced. Okay, so I'm going to go by calculating the number of moles of oxygen, right? And I have 10 moles of hydrogen gas, right? And I'm going to use the coefficient here based on this reaction. Every 2 moles of hydrogen gas is only reacting with 1 mole of oxygen gas, right? So I need to write down 2 moles of 2 moles of hydrogen gas here. Remember that they have to be consistent, so we can cross it out. And then I have 1 mole of oxygen here, so that will be 10 divided by 2, which is going to be 5 moles of oxygen gas, right? So that means you start by 7 moles of oxygen gas because that is what available, right? But you only would use 5 moles of that, right? So I'm going to say 7 minus 5, and I'm going to have 2 moles of oxygen still present when all of my hydrogen gases are gone. Okay, so let me summarize this in table. I'm a really big fan of table. It's a really easy way, kind of systematic way to see all the changes, right, as the reaction is happening. So before the reaction, I have 10 moles of hydrogen, 7 moles of oxygen, and I don't have anything for my water product. After the change happens, right, I'm going to have negative 10. I'm losing 10 moles of hydrogen gas. Minus 5, right, I'm losing 5 moles of oxygen gas, and we are producing 10 moles of water. So that means after the reaction is completed, we're going to have nothing left over for hydrogen. We're going to have some of these oxygen gases, unreacted, which is 2 moles, and we also have 10 moles of water. So I can say that my hydrogen here is the limiting reagent or the limiting reactant, and oxygen here is our excess reactant. Okay, cool. If that makes sense, take a look at the next page. Okay, now we're going to be looking at the theoretical as well as the percent yield. So in terms of the theoretical yield, this is presenting the maximum amount of product that can be formed when the limiting reactant is completely gone. Okay, now in practice, when you measure the masses of the products, right, this is what we call the actual yield. That is almost always less than the theoretical yield and can never exceed that, right? So that's why we're going to go by the percent yield, which is going to be calculated by dividing the actual yield by the theoretical yield. And we also need to multiply that by 100 because we typically express that in a form of percent. Okay, so we need to remember this equation here. Now, I want you to think about what are some possible reasoning for having the percent yield less than 100%. Okay, so we're going to answer this question in our next slide. So there are various reasons, and I'm just going to give you some of them that are very common. Okay, the first one is incomplete reactions. So the reaction may not go to completion, meaning that some of the reactants remain unreacted. Okay, another possible reason is having side reactions, right? So other reactions may happen alongside the main reaction, producing unwanted byproducts and reducing the amount of desired product. You may have loss of product during the separation or even the purification or even the mechanical loss. So when isolating or purifying the product, maybe you're doing filtration, maybe you have recrystallization or even extraction, some products may be lost. Also, you can say some amounts of the materials may stick to the containers or maybe to the filters or even to your equipment, leading to lower recovery. The other possible reason is measurements error, right? Errors in weighing reactants or products, transferring the materials, or using improper techniques can lead to discrepancies. The other possible reason is impurities in our reactants. If the reactants are not pure, the amount of the product formed may be less than expected. Maybe we have human errors, right? Mistakes in following the procedures, such as incorrect reagent addition or even the timing, can affect the yield of the reaction. And the last but not the least one is our equilibrium limitation. For the reactions that are reversible and reach equilibrium, the reaction may not go completely to the product side, leaving some of the materials unreacted, right? So these are just some, possible reasoning for having the yield of the reaction less than 100%. Okay, cool. Okay, so that brings us to the practice section. So here is the question. We have adipic acid, which is given here, right? You got the chemical formula, is made commercially by a reaction between cyclohexane and oxygen. The reaction is also balanced, as you can see. And the question is, assume that you carry out this reaction with 25 grams of cyclohexane, and it says cyclohexane is the limiting reactant. And then the question is, what is the theoretical yield of adipic acid? Okay, so I'm going to start by my cyclohexane mass using the molar mass, right? This is something that you get it from the periodic table. You can calculate that. That is going to give us 1 mole of cyclohexane. Now, according to this reaction, you can see that if you have 2 moles of cyclohexane, we're going to make 2 moles of adipic acid, right? So I have 2 by 2 here. Again, you can continue crossing out your units. And then at the last step, I need to grab the molar mass of adipic acid using the periodic table. Okay, so that is going to give me 43.5 grams of adipic acid. Now, the next part is if you obtain 33.5 grams of adipic acid, what is the percent yield for the reaction? So we already got the theoretical yield in the previous part, which was 43.5. And then here we have the kind of, the actual value, which is 33.5. You multiply that by 100, and that is going to be about 77%. Okay, I hope you enjoy this lesson. And guess what? I'm about to place an order for my burger. Don't forget to like this video if you're also a fan of cheeseburgers. Thank you so much. Take care of yourself. I'll see you on the next video very soon. Bye bye for now.